The properties of light have been studied for a very long time. Its wave-like nature, governing equations, and interaction with objects like lenses and polarizers have been well explored. In the field of optics, some current research takes on the topic of longitudinally structured light. That means light that is designed to change certain properties like wavelength and orbital angular momentum as it propagates through space. Imagine a beam of light that follows a piecewise linear trajectory or splits on its own in midair. This can be achieved by using the principle of superposition and overlapping many beams of light with the right boundary conditions, including phase and wavelength. Since light has to follow the wave equation, not every pattern of light that we want can be created perfectly, but we can usually get very close. We can define a scalar function in space to be what we want the light waves to look like and call it phi. Now we can define another function, psi, to be any scalar function that obeys the wave equation. We do not know yet what psi actually is, but it represents a physically possible light pattern in our space. To find psi, we need to use some variational calculus using an adjoint function lambda, which we define to equal 0 on the boundary of the field. If we call an error functional epsilon, as defined here to effectively be the overall difference between our desired function and our actual function, we know that the error reaches a minimum when its first order change is 0 for any variation in psi. This gives us a fourth order differential equation we can use to find lambda, which can be plugged into this equation to find psi. Once psi is known for all values of x, y, and z, it is known at the boundary. A spatial light modulator was used to set the intensity and phase of light at the boundary to match the conditions that we found. A 4F system was used to demagnify the transverse plane of the optical field, and the light pattern at different points along the propagation axis was recorded with a CCD camera. As an example, a beam was designed that splits in two horizontally, propagates for a certain distance, then each part splits in two vertically. Here is a visualization of the theoretical trajectory of the beam, or the trajectory that we want to get as close to as possible. And here are the measured transverse intensity profiles of the experiment at different points along the axis of propagation. As you can see, the original central spot splits horizontally at a distance of around 30 millimeters, then the pattern splits again vertically at around 50 millimeters. On the right here is a reconstruction of the intensity profiles, stitched together to show the three-dimensional pattern. Let's see what else is possible. How about a piecewise linear trajectory that can change direction in midair? Here are the intensity profiles of a beam that propagates straight for around 16 millimeters, moves at an angle in the XZ plane for 32 millimeters, travels downward in the YZ plane for another 28 millimeters, then returns to traveling straight in the Z direction. A side-by-side look at the intended path and the reconstructed measured path show that the two match quite well. We can also make the beam follow a curved path in free space. By comparing a longitudinally structured curved beam to an airy beam with the same curvature and spot size, our structured beam is able to mostly eliminate the side lobes. For another example, here is a beam whose 3D trajectory can't be contained in a single plane. It starts moving upward in the YZ plane, and as it decelerates in the Y direction, it starts to accelerate in the X direction. We say that the shape of this beam has torsion. At this point, I want to pose a question for you to consider. Aren't we taught that light has to move in a straight line in air? How can we reconcile these demonstrations with the knowledge that light must transmit its energy along a straight path? Think about it and see if you can figure it out. In addition to changing the trajectory of beams of light, we can also look at altering properties like the orbital angular momentum of a beam of light along its trajectory. To demonstrate this, a beam of light was designed that starts its path with 0 orbital angular momentum, then changes to a value of +1 after a certain distance. After propagating less than 100 millimeters, the beam looks much like it did in previous tests, but after a point, the phase distribution clearly begins to change, and the beam becomes a vortex beam with a topological charge of +1. Like some of the previous examples, this beam also follows a curved path in space. Being able to engineer the trajectory and orbital angular momentum of beams of light has very useful applications in fields like optical micromanipulation, where finely designed light rays can be used to move microscopic particles. And as we will discuss in another video, creating beams capable of bending around obstacles is very promising for the field of imaging, coming up with new ways of capturing and transmitting information. I have included some relevant papers for your convenience. Thank you for your time.